Welcome back to Chapter 4 on continuity. In this final section, we extend our notion of a limit so that it works in the extended real number system. Up to now, when we wrote that f of t tends to a as t tends to x, both a and x were ordinary real numbers. Here we allow either one or both to be plus infinity or minus infinity. The clever move is to restate the whole definition in the language of neighborhoods, which lets a single sentence cover every case at once. Let's see how it works. Here is our plan. We start by recalling why we want to reach into the extended reals at all. Then we define neighborhoods of plus and minus infinity. With that in hand, we give one unified definition of a limit that covers finite and infinite cases together. Finally, we state the arithmetic rules for these limits and note the forbidden combinations that are simply not defined. Let's begin with the motivation. Let's recall where we stand. Back in definition 4.1, we explained what it means for f of t to approach a value a as t approaches a point x. In that original setting, both the target a and the point x were ordinary real numbers. The first bullet on the slide records exactly that starting point. Now let's ask what is missing. In practice, we constantly want to talk about behavior at infinity. What happens to f of t as t runs off to plus infinity? When does a function blow up to plus infinity as t approaches a point? The second bullet captures these wishes. We want to allow the point x, or the target a, or both, to be plus infinity or minus infinity. But our old definition only knows about real numbers. We need to enlarge it. Here is the key idea, and it is a beautiful one. Instead of writing a separate definition for each case, we rephrase the original definition 4.1 purely in the language of neighborhoods. Once closeness is expressed as lying inside a neighborhood, we are free to define a neighborhood of infinity as well. A single sentence will then handle finite and infinite limits together. Let's first remind ourselves what a neighborhood of a real number is. Before extending anything, let's recall the familiar case shown in the blue definition block. A neighborhood of a real number x is just an open segment centered at x, running from x minus delta to x plus delta, where delta is some positive number. Saying that t is close to x is the same as saying that t sits inside one of these segments. The smaller we take delta, the closer we force t to be. Now we want a similar notion of closeness for plus and minus infinity. Here is the new definition. A neighborhood of plus infinity is any ray of the form open interval from c to plus infinity, that is, the set of all real numbers larger than c. Similarly, a neighborhood of minus infinity is the set of all real numbers smaller than c. Think of c as a cutoff. To be close to plus infinity simply means to be beyond the cutoff, that is, bigger than c. The larger we choose c, the deeper into the positive reals we force the point. This is the perfect analog of shrinking delta in the finite case. Let's picture it. This picture lines up the three kinds of neighborhood. On the top line, in blue, is the familiar neighborhood of a real number, x, a bounded segment around x with open endpoints. On the middle line, in orange, is a neighborhood of plus infinity, a ray that starts just past the cutoff c and shoots off to the right forever, shown by the arrow. On the bottom line, in green, is a neighborhood of minus infinity, a ray that starts just before C and runs off to the left forever. The bounded segment and the two unbounded rays now play exactly the same role, which is what lets us unify the definition of a limit. Here is the unified definition, and notice how compact it is. We are given a real function f on a set E, and now both the target A and the approach point x may be real or infinite. We say f of t tends to A as t tends to x if the following holds. For every neighborhood U of the target A, we can find a neighborhood V of the point x, such that V actually meets the domain E, and so that f of t lands inside U for every t in that overlap other than x itself. Read it slowly. It is the usual challenge and response. You hand me a target neighborhood. I must supply an approach neighborhood that forces the outputs into your target. A natural worry. Did we change the meaning in the familiar case? The answer is no, and the gray block records that reassurance. When both A and X are real, a neighborhood U of A is just an interval of radius epsilon. So the condition f of t lies in U is exactly the statement that the distance from f of t to A is less than epsilon. Likewise, a neighborhood V of x is an interval of radius delta, so requiring t in V with t not equal to x is exactly the condition 0 less than the distance from D to x less than delta. As the note at the bottom of the slide stresses, that strict 0 on the left is precisely the requirement that t is not equal to x. The limit ignores the value of f at x itself. So the new definition reduces word for word to the old epsilon delta definition. Nothing was lost. Let's make the infinite case concrete with a picture. The blue curve is the graph of f of t equals 1 over t squared. As d approaches 0 from either side, the curve climbs without bound. Now play the game. Your target neighborhood U of plus infinity is everything above the orange dashed line at height C. My job is to find an approach neighborhood V of 0, the green segment on the t-axis, so that the curve sits above the line for every t in that segment. Notice the small open circles at the two ends of the green segment. They show that V is an open interval, and the center point 0 is left out as well, since the definition only looks at t different from 0. The amber block shows the choice. Pick delta so that 1 over delta squared exceeds c. Then any non-zero t closer than delta gives an output above c. That is precisely f of t tends to plus infinity as t tends to 0. The previous example let the target be infinite. This one lets the approach point be infinite, which is the other half of the section title. The amber curve is EF of t equals 1 over t, and we ask what happens as t runs off to plus infinity. Now the roles swap. Your target neighborhood U of 0 is the blue band hugging the horizontal axis, stretching from minus epsilon up to plus epsilon between the two dashed lines. My approach neighborhood V of plus infinity is the green ray on the t-axis, everything past a cutoff c. The amber block shows the choice. Take c equal to 1 over epsilon. Then for every t beyond c, the curve has dropped inside the band, so the size of f of t is below epsilon. That is exactly f of t tends to 0 as t tends to plus infinity. Same definition, different case. Now the arithmetic. This is the analog of Theorem 4.4 from earlier in the chapter, and Rudin tells us the proof offers nothing new. So we focus on the statement. Suppose f of t tends to A, and g of t tends to b as t tends to x, where the values may now be infinite. Part A, shown below the red block, is uniqueness. A function cannot approach two different limits, so if f of t also tends to some a prime, then a prime must equal a. The crucial phrase in the theorem is, provided the right-hand sides are defined, and we will see in a moment why that caveat matters. Parts B, C, and D extend the usual algebra of limits to the extended reals. The limit of a sum is the sum of the limits a plus b. The limit of a product is the product a times b. And the limit of a quotient is the quotient a over b. These look identical to the ordinary rules, and that is the point. Once we accept the extended arithmetic of plus and minus infinity, the same formulas keep working. For instance, if f of t tends to plus infinity, while g of t tends to 5, then the sum tends to plus infinity, and the product tends to plus infinity as well. But there is a catch built into every line. The words, provided the right-hand sides are defined. Let's see what can go wrong. Here are the trouble spots. Infinity minus infinity, 0 times infinity, infinity divided by infinity, and any number divided by 0 are simply not assigned a value in the extended real number system. This goes back to definition 1.23, where we set up the extended arithmetic and deliberately left these combinations undefined. To see why infinity minus infinity has no meaning, picture two functions that both grow without bound. Their difference could approach any number at all or nothing in particular, depending entirely on how fast each one grows. There is simply no single answer worth assigning. So Theorem 434 carries the safety clause we kept emphasizing. The sum, product, or quotient rule holds only when the resulting right-hand side is one of the defined expressions. If you land on one of these four forbidden forms, the theorem says nothing, and indeed the limit can genuinely fail to exist or take different values. These are the classic indeterminate forms you will meet again and again. Let's gather the main ideas. First, the structural step that made everything possible. We defined neighborhoods of plus and minus infinity as rays. A neighborhood of plus infinity is everything past a cutoff c, and a neighborhood of minus infinity is everything before a cutoff. These unbounded rays play the same role that bounded segments play around a finite point. Second, with those neighborhoods in hand, definition 4.33 gave a single statement covering every case at once. For every neighborhood of the target, there is a neighborhood of the approach point that drives the outputs into it. When the values are real, this reduces exactly to the old epsilon delta definition, and when they are infinite, it captures blow-up and behavior at infinity, all in the same breath. Third, the algebra of limits in Theorem 434 carries over unchanged. Sums, products, and quotients of limits behave as you would hope, as long as the right-hand side avoids the forbidden forms infinity minus infinity, 0 times infinity, infinity over infinity, and division by 0. That completes Chapter 4 on continuity. Next, we open Chapter 5 and turn to differentiation, where these limit ideas become the engine behind the derivative. See you there.